Good day. This is Harcourt, and welcome to Harcourt University. Now, on this episode, I'm going to explain the concepts of rotary balancing and how to use the graphical method and analytical method to solve for some answers or the reaction in rotary balancing. We are talking about the forces acting on a shaft that is rotating being balanced. So some of the forces in both x and y axis should be equal to 0. That is, say, sum of forces in the x should be equal to 0, sum of force in the y should be equal to 0, and sum of moment should be equal to 0 as well. That's for plane mechanics, obviously. Now, for this diagram, we have a shaft here, right? Now, shaft you normally have pulleys on them, right? Or anything at all that is on the shaft that is transporting motion or whatever it is. So let's take a pulley for instance. So if we have a pulley around this shaft, the center of mass of the pulley wouldn't be on the same axis of rotation. The center of mass can shift from the axis of rotation, something like this. So if that happens, then you can only concentrate on the center of mass as a certain mass at certain radius from the axis of rotation. This wouldn't be different from having a stone tied to a rope and then whirling it around. Right now, if it happens this way, if you have a stone like this, the stone wouldn't fly away or wouldn't fall. It would be on this same path throughout as you whirl it around, because there is a certain force acting on the ball, preventing it from moving out. So the ball is trying to move out with a certain force Fc, which is equal to mv squared r, or m omega squared r, mv squared on r. Now, this is what we call the centripetal force. So this centripetal force here is balancing the tension in the string or the rope you are using to whirl the ball around. So in the same vein, the mass on the shaft will also experience this centripetal force. Now, it's these forces that we want to determine if the resultants due to the several masses on the shaft balance out or not. So to do that, we first have to put that in components. So first off, we've been able to understand that the masses we're going to possess centripetal force. So if I look at the shafts in this direction, I'll see them arranged in this direction. But if you look at from this direction, there will be a certain inclined to a certain angle. So if there's a shaft, then if I look at the mass, it could be inclined to a certain angle to the x-axis. So I can put the force in x and y component, right? So this one will be m omega squared r. This one will be m omega squared sine theta, m omega squared cos theta. So if I have another mass here, m2, that will be the same. So if I'm finding the forces, then I'm going to have sum of force in the x to be equal to m1 r1 omega squared cos theta 1 plus m2 r2 omega squared cos theta 2 up to mn rn omega squared cos theta n. So this means I can put it in single expression to say integral sum from I equals to 1 to n mi ri omega squared cos theta I, meaning I pick the if I is 1, I'll put it here, and then I'll have this. If I is 2, I'll have this, then I'll be adding them. So the same for the y. So that will be sum of force in the y will be equal to sum from I equals to 1 to n mi ri omega squared sine theta I. Now, when I'm done, then I have to take moment at any point. So suppose I'm taking moment here, then the distance from here to here is L for mass 1, and then L for mass 2 will be 0. Now let's take the moment here. Then I'm going to have from here up to here, right? So you rather start from the point you're taking the moment about to the mass. So you start from here up to here, rather, and then from here up to here. So this one will be L2, this one will be L1. Okay, so if I want the moment, this one will be m omega squared r l, right? So the sine component should be m omega squared r l sine theta, m omega squared r l cos theta. which is to say sum of moments for x will be m1 r1 l1 omega squared cos theta 1 plus what m2 r2 omega squared cos theta 2 up to what mn rn ln omega squared cos what theta n, which is similar to this, just that we are introducing L. So we can say in general we have sigma mi ri li cos theta I, and for y we equal to what sigma mi ri li sin theta I. All right, so our duty is to have these terms and then just be substituting. Now we are going to use this concept to solve this problem. Okay, that if we come to the equations we've generated, for the force to be equal to 0, you realize that the omega doesn't have I. Why? Because the angular velocity of the shaft is the same for all the masses. So we didn't have any respective angular velocity for an individual mass. So we can factorize the omega squared out. And this is to say that for the force to be balanced in the x direction or any direction, or the moment to be balanced, omega doesn't play a role. The focus is just mi ri and then of course theta I, and then the over here to mi ri li for the moment. So I'm just going to create a table that will have the force and then the moment in it for this particular question. Okay, so we have, let's say, positions here. Let me use black pen. So you have the masses, you have the radius of rotation. So this one can say kilogram, this one meter, and then mr, you have kilogram meter. Then the L, what is meter? That will be mRL, and then theta. This one will be kilogram meter squared. So we say sum of force should be equal to sum of force in the x direction is sigma mi ri omega squared cos what theta I. Sum of moment force in y sigma mi ri omega squared sin theta I. And sum of moments in x, we have what? Sum mi ri li li omega squared cos theta I, and then okay, so the positions we have at A, at 1, at 2, at 3, and then at B. Now the A and B are just bearings, so they are going to experience some amount of force from the unbalanced mass, the dynamic unbalanced forces from the M1, M2, and M3. Now, since they are forces, we can find the equivalent mass, because if you look at here, the equivalent mass times radius, right? Or radius of rotation, because here the angular velocity squared, we said we can factorize that out, right? So we don't know the mass at A, we don't know the radius at A, but the equivalent mass times radius at A, you make it at RA. And we talk about this later. The mass 1 is 40 kilogram, mass 2 is 45, mass 3 is 50. B has no mass. The radius of rotation for 1 is 40 millimeters, so 0.04. For 2 is 0.038. This one is 0.035. This one is dash. So the forces 40 will give us, for 1 we have m1 r1 40 times 0.04, that's 1.6. The next one, 45 times 0.038, that is 1.71. Then we have 50 times 0.038. We have 1.9. And then we have RB here. Okay, so we are going to take moment at A, right? Take moment at A. Now, from here to here, going to your right to be positive, going to your left to be negative. All right, in the sense that though this one will give you counterclockwise and this will give you clockwise, but I'm making both negative. The down one, the negative will come from the angular positions. So if you make it negative from the onset, we will change everything. So let's just maintain going right is positive, going left is what? Negative. So at RE, if you take a moment at RE, the moment arm for A will be 0. For mass 1, it's just what? 950, which is 0.95. Mass 2, 0.4. Mass 3, so 1.45. And then RB will be 1.9. So MRL, this one will be 0. We have $35. Okay, so I made a mistake earlier. This is supposed to be 1.75. 45 times 0.038. Okay. All right, so 1.6 times 0.95, that is 1.52. 1.71 times 0.4, that's 0.68. 4. Then 1.75 times 1.45, that is 2.53. 54, let's make it this one. And then this one will be 1.9 RB. The angular orientation, this is theta A for mass 1. From the positive x-axis is 90. Mass 2, we have 180 plus 45. So 180 plus 45 will be what? 225. And then mass 3, that is 300. And then mass 4, RB, we don't know, so theta B here. Okay. All right, so now we are done with the diagram. So we can either use the analytical method to solve for this or use the graphical method. So I'm going to use the analytical method to solve. Then we will use the graphical method to solve for the same problem. Okay, so let's begin with the analytical method. Let me bring in. Okay, so for the analytical method, since the so we took moment on array because we want to minimize the number of unknowns. So since array, we took moment on array, realize that the array wouldn't show in the moments that terms. So you would first have to use the moment to find RB. So let's do that. So first of sum of moments this is black. Sum of moments in the x direction is equal to what? 0 if the system is balanced. Right, so we have 0 cos theta A plus 1.52 cos 90 plus 0.684 cos 225 plus 2.54 cos 300 plus 1.9 RB cos theta B is equal to 0. So if we simplify this, this goes to 0, this goes to 0. So we have 0.684 786. And you do for the y. So the y, so the x was cos, the y is sine. So we have 0 sine theta A Okay, so from here we have 1.52 to be equal to 1.163. So equation 1, equation 2. Okay, so to find the angle, we can say equation 2 on equation 1, which will imply 1.9 RB sine theta B all on 1.9 RB cos theta B is equal to 1.163 all over 0.6786 negative, right? So you have tan inverse of 1.163 all on negative 0.786. Now I will ignore the negative and just find the acute angle and locate the quadrant. So if you are plotting this and this on the Cartesian plane, the x cos is for x, which is negative, so it will be here. And then the sine is positive, y, which is positive, which will be here. So the acute angle is always between the x-axis, right? So if you find the quadrant, then acute angle is here. So the angle will be measured from here up to what, to here. So let's find the acute angle here. So we have tan inverse of 1.163 all on 0.786. Okay, so we are having theta to be equal to 55.947. All right, so theta B will be equal to 180 minus 55.947, which is equal to, so 180 minus 55.947, and that gives us 124.1 degrees. All right, so now we know theta B. We can use that to find RB. You can use this or this, any of them will give you the answer. So to find RB, you can use equation 2. So 1.9 RB sine 124.1 should be equal to 1.163. So RB will be equal to 1.163 divided by 1.9 sine 124.1, and that will be 1.163 divided by 1.9 sine 124.1. So we are getting 0.739 kilogram meter, right? So we found the question one asked us to find the relative angle, right? So let's do that first. So now we found that for B, and we found the magnitude, force times radius equivalent for the reaction at B. So now that we know this and this, we can come to the force side to find RA. Okay, 124.1. So with the force, you're going to have, so the formula we first have, the expression is sum of forces in the S is equal to sum of mi ri omega squared cos what theta I, right? So just focus on m1 r1. So since the omega can be factorized, if you say it's equal to 0, omega squared can divide both sides, right? So just focus on m1 r1, and then for the y, that would be sigma m I r I omega squared sine what theta I. All right, so this means if we come to sum of forces in the x direction, if it's equal to 0, then RA cos theta A plus M1 R1, which is 1.6 cos 90 plus 1.71 cos 225 plus 1.75 cos 300 plus, and now RB was 0.739 cos 124.1 should be equal to 0. So if we simplify in that, this one goes to 0 obviously. RA cos theta A to be equal to 0.748. All right, now the equation one, sum of forces in the y, they're going to have is equal to 0. They're going to have RA sine theta A plus 1.6 sine 90 plus 1.71 sine 225 plus 1.75 sine 300 plus 0.73 0.739 sine 124.1 is equal to 0. All right, so simplifying that, you're going to have 0.512 or 0.513. So equation 2. So I'm going to have, you're going to have RA on RB, right? So we're going to have equation 2 on equation 1. This one will give us RA sine theta A all over RA cos theta A is equal to 0.513 all on 0.748. So tan theta A is equal to, okay, so the same expression, 0.513 all on 0.748. So realize that for this, both the x and y components have the same value, right? So for this, the On a Cartesian plane, x is positive, y is positive. So to be in the first quadrant. So theta A will be equal to tan inverse of what? 0.513 all on 0.748. And that will be 0.513 on 0.748. So we have 34.44 degrees, right? So now we know the angular orientation from as one. We can get the RA as well. So RA sine 34.4 should be equal to 0.513. So RA will be equal to RA will be equal to 0.513 all on sine 34.44, maybe 0.513 all on sine 34.44. So that gives us 0.91 kilogram meter.